Hi everyone, welcome and thanks for your interest in our work. I'm Jia from the Ohio State University. In this presentation, I'm gonna introduce our pattern-based API for mapping applications to a hierarchy of multi-core devices. Specifically, we target certain types of applications which process and react to real-time data feed and distribute processing of tasks among central and edge devices. We try to provide a general set of APIs so that these applications can be easily mapped to different multi-core environments. We find this topic particularly interesting because, first, although powerful edge devices equipped with GPUs or neural accelerators are very common today, most pervasive and inexpensive IoT devices do not have such capabilities. Yet, the multi-core structure is even more popular, demonstrating great potential to process considerable workload locally. Secondly, proper distribution of workload among the interconnected edge central devices with different configurations can greatly improve the performance of such applications. As the context of our work, we first give some general ideas on the IoT environment we are targeting. We also introduce our previous work on reduction object, which inspired our optimizations. To better understand the features of our design, we talk about 3 applications we support and experiment with during the research. Generalizing the characteristics of these 3 applications, we define a set of APIs. Furthermore, we will talk about the optimization and load balancing support by this set of APIs. Finally, we study the performance of our implementation. In the past decade, Internet of Things has quickly evolved from an idea to the prevalent edge devices in everyday life. Inexpensive single-board computers, smart routers and gateways, smart cameras and so on are widely available. Most of these devices have multi-core CPUs, some even equipped with GPUs, but most for rendering and no general-purpose interface. Often, heterogeneous edge and central devices form vertical hierarchical structure, from most powerful cloud servers on the top to sensors with limited processing power on the bottom. The connection is also heterogeneous, from fiber on the top to wireless connection with limited bandwidth and power on the bottom. Nonetheless, the applications in this context are often latency sensitive, such as real-time control and image processing. Therefore, we want to process data locally as much as we can, so that we can return the results quickly and not overwhelm the limited bandwidth. To improve the efficiency of local processing on edge devices, we seek inspirations from our previous work on reduction object. This reduction object paradigm is proposed as a highly efficient alternate for MapReduce programming. It contains 4 functions: key generation, object accumulation, object merging, and post-processing. For a given application, these 4 functions can be easily derived from Hadoop MapReduce interfaces. The difference is they work on a user-defined reduction object, which is an accumulator of values. As shown in this figure, for a given input element, a key is generated, pointing to a specific reduction object. Immediately, the input element is accumulated to this reduction object. Once all the inputs are processed, accumulators from different threads will be merged and processed, yielding the final result. Similar to standard MapReduce, this process can also be easily mapped to multi-core and multi-machine environment. However, by improving the access locality of intermediate results, reduction object paradigm achieves great speed up over Hadoop MapReduce and Spark. In our design, we want to extend the reduction object paradigm to a broader type of image processing applications. In this way, we want to improve the locality of these applications so that we can maximize the CPU and memory efficiency on edge devices. Furthermore, in the hierarchy of central edge devices, we want to balance the load for distributed tasks. Before we get to the system design, let's walk through the applications we want to optimize. First, let me introduce a few common concepts used in the applications. In target detection applications, to find a match in different parts of an image, a detection window will slide across the whole image by some fixed step, and the detection algorithm will run in each and every window. Moreover, to detect targets of different scales in an image, the application will downsample this image by different levels. Such series of downsample images form a pyramid shape. The detection will be executed on each level of the pyramid. The first application is target detection based on Haar features. Haar features can be visualized as a series of black-white rectangles. For a given detection window, we apply a Haar feature onto the image. By subtracting the sum of the pixels in the white area from the sum of the pixels in the black area, we can extract the edge information from the image. Then a decision tree will accept those information and classify the detection window as target or non-target. The detection with local binary pattern works similarly. Within a detection window, by comparing the sum of pixels in a specific square with its 8 surrounding squares, a binary serial representing the comparison result is generated. The result will also be fed to a classification tree for target detection. The third application is based on histogram of gradients. The idea of HOG is that it calculates the norm and orientation of the gradient on each pixel. Then gradients are collected in histogram through orientation binning, and the votes are weighted by the norm. The histogram of different areas are then normalized with its vicinity and coded as vectors. Inputting all the vectors in a sliding window to a support vector machine, the window can be classified as target or non-target. To capture the above applications, we extend the interfaces of reduction object with 3 functions specific to image processing. Given an input image and a downscale factor, the pyramid function will generate a pyramid of downscaled images. And in each image, we can use the window abstraction to define a series of sliding windows. Within a window, an algorithm can be defined using the reduction object paradigm. This algorithm can automatically be mapped to all available cores. We also provide an abstraction for 2D convolutions, such as the one we discussed in Haar feature extraction. Additionally, user-defined transformations are also provided for better compatibility. When we use the pyramid operator, the same calculation is carried out on different scales of one image. Therefore, the complexity of one level is proportional to the size of the image, making it possible for us to estimate the workload. Through a one-time load test, we can also estimate the processing power of each central or edge device. Then the pyramid workload can be evenly distributed across the hierarchy of devices. In this way, we can minimize the global latency of the multi-level target detection applications. For sliding window applications, we define a cache to store results across adjacent windows. In most cases, the adjacent windows share a large portion of common data, so it is very likely for the latter window to reuse the results from the former. Once a dependency is defined for adjacent windows, the system can sort out a proper execution order so that the redundant calculation can be avoided. For example, the same hard feature is applied for adjacent windows, and the step between these two windows is just 1 pixel. As we can see here, obviously the calculation results in the red circle can actually be reused. There are 3 levels of parallelism in our implementation. The pyramid operations, as we have discussed, is distributed across different hosts. On each device, we map the reduction object paradigm and the window operations to different cores using OpenMP. Finally, on the lowest level, we further optimize the applications with regular access patterns using SIMD instructions. For example, the calculation of vertical and horizontal gradients in the HOG feature selection algorithm can easily be SIMDized. Finally, we want to talk about our experimental results. In the first experiment, we carry out performance and scalability comparison between our implementation and OpenCVs. Both versions of all 3 applications are tested on a Raspberry Pi and a cloud server. The second experiment tests the load balancing capability of our implementation. We set up a powerful desktop running as the backend of 6 Raspberry Pis. We manually vary the workload on different devices and measure the latency to see if our system works under the lowest latency. On a single core of Raspberry Pi, our implementation is 17 to 35% faster than the implementation of OpenCV. When the number of cores grow, our implementation shows comparable scalability to OpenCV's implementation. When it comes to a server processor, our implementation is 27 to 39% faster on a single core. From 1 to 16 cores, for hard and LBP-based detection, our implementation demonstrates a speed up of 9 times and 7 times, which is comparable with OpenCVs. For the HOG SVM detection, our implementation shows better scalability than OpenCVs. This advantage mainly comes from the good scalability and locality of reduction object paradigm. In the load balancing test, our system estimates that the desktop has 15 times the processing power of a single Raspberry Pi, and we have 6 Raspberry Pis, so the system puts 2.5 units of workload on PC and 1 unit on Raspberry Pis. The dashed green line in the figure shows the estimated sweet spot of workload distribution. The curves in the figure shows how the actual latency changes as we vary the workload distribution. As we can see, both cases are working under the optimized latency. To summarize, our implementation shows better scalability and lower processing time on both cloud and Raspberry Pi compared with OpenCVs. Moreover, we also come up with a reasonable division of workload across hierarchy of devices. That's all about our work. Thank you again for your time.